All right, so these are notes for the last lesson in chapter 5. And there is another lesson, I should say the last main lesson in chapter 5. There's an optional lesson after this. But this is the lesson for the last main lesson in chapter 5, which is on arithmetic sequences. So first, what's a sequence? A sequence is just a list of numbers. It's literally a list. So they're discrete items, they're not continuous, although they may go on forever. But it's a list that always has a starting point and then just continues, and it may stop, it may go on forever. An arithmetic sequence, that extra little term there, that's a list where each term has the same difference from one term to the next. So maybe I'll highlight this different. The term arithmetic sequence, which is what we're focusing on, that's where the difference from one term to the next is always the same. So for example, what we see down here below is an example of a sequence. And so a few things I can say. -5 is the first term, and we usually just call that T1. So 1 is the second term, 7 is the third term, so T3, 13 is the fourth term. I then skip a bunch of terms, and then we get to 2047, which I don't know what term number that is, so quite often we just call that Tn, the nth term. And so notice, what's my common difference? What is the difference from one term to the next? Well, I go from here to here, I can see I go up by 6. And notice it's the same every single time. If it wasn't the same every single time, then it's still a sequence, but it's not an arithmetic sequence, which means it's not what we're focusing on. And that's 6, that it's going up by every time. We call that the common difference. All right, so that phrase, common difference, is pretty easy to figure out if it's if it truly is an arithmetic sequence. Essentially, you just take any term and subtract from it the one before. And so, common difference, we usually call that just D. If we are too lazy to write out all those letters for common difference. And again, it's always you can find by taking just any term, and from that, subtracting the previous term, the one before that. And you could express this as a formula, which I think is kind of silly because it's such a simple formula. So let me just kind of put brackets around this. Any term minus the one before it. All right, so for example, looking at this arithmetic sequence right here, the fifth term would be found by finding the fourth term, 13, and in this case adding 6. So I can say for this one here, the fifth term is going to be the same as just 13 plus 6. So the fifth term is 19. So the sixth term would be 19 plus 6, so 25. And we get the idea. Okay? Now, what term is 2047? That last term on that list there, I just called Tn right now. We can figure out what term that is in a few different ways. One way is just to keep adding 6 and making a list until we get to 2047. For big numbers like that, I don't recommend that, but that is possible. But there's definitely more efficient ways of getting to that if you have an arithmetic sequence. But for the time being, I'll just leave this first example here. All right. So an arithmetic sequence, a common difference, the term, T1 represents term 1, and so on. All right. So in general, though, if we just have these terms, term 1, term 2, term 3, term 4, and so on, all the way up to some term. If it is an arithmetic sequence, again, that means as we go from here to here, we're always adding the same amount. If you ever notice in a sequence that when you go from one term to the next, you're not adding the exact same number every time, that means either you've made a mistake or it's not an arithmetic sequence, which means all these things I'm about to talk about don't apply. So how could we find a way of generalizing this pattern? Or how can we find a way of getting to larger term numbers without literally counting every single one? Well, I'm going to start by making a simple little list here. That might seem kind of silly at first. So notice, I'm going to say something really crazy here. The first term is the same as the first term. Pretty crazy. Okay. More importantly, though, the second term is the exact same as the first term plus the common difference. The third term is the same as the first term plus the common difference twice. So I could put d plus d, or that's 2d's. I'm going to go 2d, 2 times d. The fourth term is going to be the same as the first term plus the common difference 3 times. And you can literally see, to get to that fourth term, if I start the first term, I add d 3 times. And so I'll do one more like this, t5, equals t1 plus 4 of those. And I can now generalize this, because notice every single time, if I actually go back, I can even put a little 1 in front of t2 and say t2 equals t1 plus 1 times d. And if I notice this little pattern here, 4, 3, 2, 1, continued up here, it's not wrong to say the first term is the same as the first term plus 0 times d. And the important thing is those numbers I've highlighted in yellow are all exactly 1 less than the term number. Right? Every single time the term number we see is 1 more than what I have to multiply d by, or what I've highlighted in yellow. So I can generalize this quite nicely. And that's what I'll do right here. So in general, we can say the nth term is always the same as the first term times, not n times d, n minus 1 times d. N minus 1 is what I've been showing you highlighted in yellow. The nth term is what I've highlighted in blue. To kind of compare these together, or a slightly more common way of writing this, we say, oh, sorry, I forgot to put a plus sign right here. Plus, there we go. Say t1 plus, we usually put the d first, d times n minus 1. And really, all this is doing right here is summarizing this relatively pleasant relationship right here. Okay, and again, this is true for any arithmetic sequence. As long as there's a common difference going up by the same number each time, then this is always true. Okay, so now how can I use this to answer this question? How many terms are in this sequence? So I have 12, 7, 2, skip a few, negative 428. So again, I could keep subtracting down, and then I can see pretty quickly the common difference is not 5, it's negative 5. Okay, and so on. So that's my common difference. So it's not a terrible idea. Well, it's not utterly terrible to just keep subtracting 5 and just keeping track. Granted, you're probably going to lose track at some point. So now I can use this formula, this general form right here. I can use this to pretty quickly figure out how many terms it would take to get to negative 428. So the way I'll do that is first just write this down again. So Tn equals T1 plus d times n minus 1. In this case, if I go back to my relationship up here, my sequence, I have T1, T2, T3 is 2, and again, I'll put Tn for 428. So I don't know what term number that is, but I know the term is negative 428. And notice the difference. The term number I don't know. I don't know how far it is along in the list, but I know what the term is. The term is negative 428. And so I can go back to my formula right here, my relationship, and instead of Tn, I can write negative 428. I know the term, I just don't know what n is. And I know the first term. The first term is 12. And I know the common difference. The common difference is negative 5. So instead of putting, I could put plus negative 5 right here. However, adding negative 5 is the same as subtracting 5. So I'm just going to put take away 5. I think that's simpler. And then n minus 1, well, that's I'm trying to figure out n. So now notice I have an equation that has 2 sides to it and just one variable I don't know, which means I must be able to solve this using the sort of things we reviewed near the beginning of the course. So what I would personally do is I would distribute the negative 5 first. Keep in mind there's always more than one way of doing this. So I have negative 5n plus 5. Then I have a few choices here. Let's combine these two together to make it a little bit simpler looking. So negative 428 equals, instead of 12 minus 5n plus 5, I'll just put 12 and 5 together, so 17 minus 5n. I'm going to subtract 17 from both sides next. And for that, I get negative 445. Definitely can use a calculator, equals negative 5n. And finally, I want to divide both sides not by 5, but by negative 5. And so I get n on one side, and negative 445 divided by negative 5 is a positive number, which is 89. And it's great that it's positive. If you ever get a negative term number, that doesn't make sense. For a sequence, your first term is always t1. So you can never get a fraction for your term number. You should never get a negative for your term number. You should never get 0 for your term number. So I now know, if I look back at this sequence here, negative 428 is the 89th term. And so I would have to keep subtracting 5 over and over and over and over and over again to get to that. All right. So let's look at this. I have here a graph showing the relationship between the cost of hiring a plumber over the number of hours. And so I'm just going to put time down here in hours, and this is cost. So time is the independent variable, cost is the dependent variable, which makes sense. How much does it cost to hire a plumber? It depends on how long the plumber is there for. So I want to know, what is the general term? And again, the general term is what I have right here, right? That's or the equation that summarizes the relationship. All right, and so what is the general term for this? Well, let me start with that very basic formula. So Tn equals T1 plus D times n minus 1. And so let's look at a few things here. I can see T1 is 118. All I need now is the common difference. So how much does it go up by from here to here, from here to here, from here to here? All I got to do is pick any number and subtract the one before it. In this case, I can see it's going on up by 28 every time. So D equals 28. And now I can express this relationship as an equation. I can say Tn, or if I want in a moment I can say cost, but for now I'll just say Tn equals 118, the first term, plus the common difference, 28 times n minus 1. Now while I'm at it, I might as well clean this up a little bit. What I have here is not wrong, but it's a bit needlessly messy. And I say needlessly messy because I can distribute the 28 here and then combine like terms. So why don't I do that? I get Tn equals. Right, and now I can combine these two. Oh, sorry, I got double equals here. I'm a bit tired this morning. There we go. So I got these two like terms here, 118 and negative 28. I might as well put these together. And so I get Tn equals 90 plus 28n. Or, and that's great, what I have there is great. That's what we call the general term for this relationship. However, if we want, I'd also maybe encourage us to use different variables that are more specific to this question. Because what did n stand for? N was the time. It was the number of hours. What was Tn? That's my cost. And so while this is totally fine, I'm also going to write it like this. I'm going to say cost of hiring a plumber equals 90 plus 28 times time. Because again, I have time here and cost right here. However, again, these equations are all equivalent. And so which leads me to this question, what does the constant and coefficient in the general term represent? So first of all, the constant is the 90. It's the term that doesn't have a variable. No matter what n is, or no matter what t is, if you look at this equation right here, the constant never changes. It's always 90. And that represents the cost of just the plumber arriving, basically. So the constant represents what we call the fixed cost. So that's the fixed cost of hiring a plumber. Kind of like the fee you would pay just for them to drive there. The coefficient, which is the number multiplied to the variable. So in this case, it's the 28, which we can see in either of these equations. The coefficient, that represents the charge per hour. In this case, $28 per hour. So we have $28 per hour, and which is actually, hiring a plumber is far more than that, and the fixed cost is $90. And we can see that those numbers in the equation, that's what they meant here in this scenario. And we'll start to look at these sort of things a lot in the next chapter. So the last problem. The first four terms of an arithmetic sequence have a sum of 12 and a common difference of 8. What are the four terms? All right, chances are you read this and it's hard to know where to start. So if you ever don't know where to start with an arithmetic sequence, why not first make a sort of structure for the sequence? And by that, I mean I know there's four terms, so I'm going to write four little blanks. Comma, comma, comma. Okay, and I'll call this T1, T2, T3, T4. Okay, so we know that, the first four terms. We know they have a sum of 12. That means if I add these all up, 1, 2, 3, I know I'll get 12. So why don't I put that in? I'll put plus signs here. I know if I add these all up, I get a sum of 12. And I know the common difference is 8. So I'll just show that as I usually show it here like this. I know it's going up by 8 every time. If it was going down by 8, the common difference would be negative 8. Okay, so I got now a decent amount of my structure kind of set up here. So I'm trying to find the first four terms. Well, why don't I start with, if I look at my sort of setup here, I know I'll just call this T1. Okay, that's my first term. My second term I know is going to be the same as T1 plus 8. My third term is going to be the same as T1 plus 8 or plus 16. And on my third term is going to be the same as the first term, plus 8 plus 8 plus 8 plus 24. So now what I have up there, it's getting a bit messy, so let me write it a bit neater. I know I have an equation. I know that T1 plus 8 plus T1 plus 16 plus T1 plus 24 must all equal 12. And again, this 8, this 16, this 24, they're all like terms. They all come back to the repeated number of times the common difference is added. And all these are like terms as well. T1, 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 T1. So combining like terms together, I have 4 times T1 plus 8 plus 16 plus 24 is 48 equals 12. And suddenly, what seemed like a pretty confusing question perhaps with how to start is quickly getting much, much simpler. And that T1 is just my unknown. And so I'm going to subtract 48 from both sides. So 4 times T1 equals negative 36. Divide both sides by 4. And I can see my first term. So my first term is negative 9. Now, what was the question asking? The question is asking, what are the four terms? So I now know the first term is not negative 9. So let's now answer the question. So I'll say, therefore. I'll just put 4 little blanks. 1, 2, 3, 4. My first term is negative 9. And now I can figure out the rest by just adding 8. So if I add 8 here, I get negative 1. So that's my second term. Add 8 again, I get positive 7. Add 8 one more time, I get 15. And those are my four terms. Right? So it seems pretty open, perhaps pretty confusing at first, mainly because it's, you probably have to read it a few times, and it's just one sentence, really, the setup for the question. So there's a lot of terminology in there. Required in the end, not a ton of algebraic work, not at all. All right, and that finishes this lesson. So